This is a video about component balance. In some of my previous videos, I talk about how to apply mass balance for a system with changing mass. Component balance or specie balance is also a type of mass balance. When there are more than one component in a system, we can apply component balance for each component. For example, as a molar balance or a mass balance. So let's start component balance with mathematical modeling minds. The component balances can be written as a mass balance or a molar balance. Both of these methods are important depending on the system we are dealing with. For example, if we are writing a component balance for a biochemical system, component mass balance is used most of the times, and while dealing with chemical reactions, component molar balance is used. In component balances, rate of mass or molar accumulation is equal to rate of mass or moles coming into the system minus rate of mass or moles going out of the system plus rate of mass or mole generation. Practically, when we are dealing with fluid systems, it is very common to use concentration of a component in specifications. So let's have a look at how we can deal with concentration instead of mass or moles. Molar concentration of component X is Cx and it is equal to moles of X, Nx, divided by total volume V. The mass concentration of component X is ρx and it is equal to mass of X, Mx, divided by total volume V. So I have written the component balances using molar concentrations and mass concentrations. And when we are dealing with flow rates, instead of total volume V, we can use volumetric flow rate V dot. We can deal with accumulation term, inlet term and outlet term. But how are we going to write formula for generation term? Next we are going to have a look at how it is solved. Let's consider a reactor with input components A and B. A and B are well mixed inside the reactor to form the new component AB. The reaction rate R1 is given by K1 CA/CB. R1 has units of moles per cubic meter per second. The concentrations of A and B have units moles per cubic meter. So, the reaction rate constant K1 has units cubic meters per mole per second. K1 is a function of temperature and units of K1 depends on the order of the reaction. Okay, so now I am going to write a molar balance for component A. As I mentioned earlier, it is written as the rate of accumulation of A in the reactor is equal to rate of A coming into the reactor minus the rate of A going out of the reactor plus the rate of generation of A. N dot A gen is equal to capital RA times V. Capital RA is the rate of generation of A per volume per second and capital V is the volume of the reactor. So how are we going to find capital RA? Consider the stoichiometric reaction A plus B is forming AB, which has a reaction rate of R1. Then rearrange it so that the reactants are having negative sign as they are consuming inside the reactor and the products are having positive sign as they are formed. Then I can put the stoichiometric equation in the matrix form. The matrix that represents the stoichiometric values is called the stoichiometric matrix. The rate of generation of components per volume is given by capital R and it is equal to the transpose of stoichiometric matrix times the rate of reaction simple R1. So we can write the rate of generation of A per volume per second as minus R1. Like that, capital RB is equal to minus R1 and capital RAB is equal to R1. Next, the component balance for A can be written like this. What if we have set of reactions happening inside the reactor? Assume there are two reactions taking place inside the reactor. A and B combines to form AB with reaction rate R1. AB and A combines to form A to B with reaction rate R2. I first rearrange the equations and write the stoichiometric matrix S for the components A, B, AB and A2B. Remember to keep the order of the components when writing the matrix. Then I can put the two stoichiometric equations in the matrix form. The capital R of each component is written as a matrix equation which is equal to the transpose of the stoichiometric matrix times the rates of two reactions. Finally, I can write capital RA is equal to minus R1 minus R2, capital RB is equal to minus R1, capital RAB is equal to R1 minus R2, capital RA2B is equal to R2. And these are the component balances for each component in the reactor. We can use the equations developed for capital RA, capital RB, capital RAB and capital RA2B to substitute for the rate of generation of each of them. Finally, we can write reaction rates in terms of reaction rate constants and concentrations of reactants. I first presented how we can deal with component balances when we have molar concentrations. Now I am showing you a general biological reaction where we deal with mass concentrations. This is a simple form of a biological reaction which involves the function of cell growth. S is the substrate, N is the nitrogen, O is oxygen, capital X is the bacterial cells, and P is the product. Water and carbon dioxide are also formed as a result. Lowercase letters show stoichiometric coefficients. Mu is the specific growth rate of cells which has the units of number of cells per time. This equation is called Monod equation and Ks is Monod constant for substrate. When there are more than one substrate, the growth rate depends on each of them. Mu max is the maximum specific growth rate of cells. Cs, Cn and Co are substrate concentrations. Usually the substrate concentration is given by kilogram COD per cubic meter. COD is the amount of oxygen consumed to chemically oxidize organic compounds to end products. Nitrogen and oxygen concentrations are given in kilograms per cubic meter. Monod constants have the same units as the substrate concentration unit. Rate of cell growth Rx is given by mu times the concentration of cells Cx. It has units of kilogram COD per cubic meter per time. In biological reactions, we usually specify the yield coefficients. Yxs is the cell mass yield coefficient and Yps is the product yield coefficient. They are defined with molar mass m and stoichiometric coefficients. In the same way, you can define Ypo, Ypn and so on. Here I have presented the component balances for cells, substrate and products in the bioreactor. First, I have presented the component balance for cells, which is represented by capital X. The rate of generation of cells is given by Rx and it is equal to mu times Cx as I explained before. Next, I am applying mass balance for the substrate S. The rate of generation of substrate is Rs, but actually substrate is not generating, it is consumed. If we only consider the cell growth by substrate, we can put Rs as a function of cell mass yield coefficient and growth rate of cells. But in reality, Rs is estimated based on cell growth, product formation, and cell maintenance. But I am not going to explain it further at this point. Finally, I have presented the mass balance for products. The rate of generation of products is equal to Rp and it is stated using the yield coefficients and rate of growth of cells. This is the end of this video. If you really like the content, give thumbs up and subscribe for the channel and press the bell icon for new video notifications.